Okay. Let's record first. Okay. All right. So when we do the classification, okay, on the classification topic, we have mentioned that the most common method that used to classify a control system is based on order. Okay, so we have looked on the first order, and today we're going to look on the second order. Okay, similar to first order, we're going to learn about the behavior of second order, the parameters, the design parameters, and also how to determine all the parameters. All right, so first we start with the general transfer function of a second order. Okay, so this is given in this block diagram here. So a general transfer function for a second order system is represented by k omega n square over s square plus 2 zeta omega n s plus omega n square. Okay, so here we can see there are three parameters, k, omega n, and zeta. All right. And when we said that this is general transfer function, so we are going to look at this term here. Okay, it must be 1. Okay, you cannot have 10s square, you cannot have 5s square. You have to make sure that the term is s square only, 1s square. All right, so that is similar to the first order. We need to make sure that the first order transfer function must be 1 plus ts. Okay, so for second order, we look at the s square, it must be 1s square. All right, so the three parameters are k, which is the system gain, which is actually the same as k in first order system. Okay, meaning it will relate the output to the input at steady state. Okay. And then the second parameter is omega n, which is undamped natural frequency. And we know that omega n is a parameter that we need to know in order to avoid the system to become damaged if we are operating the system in the natural frequency region. Okay, we want to avoid resonance. Okay, so we already know that resonance will occur when the frequency of the system is in the region of frequency of natural frequency. Okay, so we need to avoid that natural frequency region so that we'll be able to make sure that our system will safely operate. Right, that is omega n. Okay, and then we have zeta, which is damping ratio. Okay, so it is damping ratio is a element in the system that will damp the energy in the system. Okay, if any system does not have a damping ratio, meaning it will continue to have a displacement, it will continue to vibrate. Okay, it will not stop. Okay, that is happen when there is no damping in the system. Okay, so damping ratio here is energy that we are able to damp the energy of the system, meaning by having damping ratio in our system, the energy will slowly be reduced, and then it will stop. It will stop, meaning the displacement will stop or the vibration will stop, because we have energy that will try to stop the movement of the system. So the energy is actually given by damping ratio. The higher the damping ratio, meaning the higher the energy that can damp the energy of the system. All right, so these three parameters will determine the response of second order. Okay, meaning the response of second order will depend on these three parameters. Okay, how much oscillation will occur in the system, the how fast the response of the system. Okay, so all that will be based on the value of K, zeta, and omega n. Okay, so that's why this K, zeta, and omega n is also known as a design parameter. Okay, we need to choose the value of K, zeta, and omega n so that the system that we design will be able to provide the output behavior as what we want. Okay. All right. So in second order system, the example of second order system is any mass spring damper system. Okay. So basically if it contains mass, so here we're going to have md square. Okay, md square x there. All right. So there will be a second differentiation term. Okay, there is d square there, second differentiation term. So the system will become second order system. Okay, second order system when it has d square, s square. Okay, so that is a second order system. All right. So we're not going to derive the ODE equation for this system. Basically, in order to get the time response equation, we need to do the same step as what we have done before. Okay, ODE, Laplace, okay, and etc. until we have inverse Laplace. Okay, so we get the YT. Okay, so the YT is the function in time that will explain the behavior of the system. Okay, so we're not going to do that for the second order. Okay, so basically for the same transfer function, K omega n square over S square plus 2 zeta omega n S plus omega n square. Okay, we apply a unit step input. Okay, and we consider K is equal to 1. And then we do all the steps just now. We do the ODE, we do all the Laplace transform and etc. until we get YT. So this is the equation that will be derived from the step just now. Okay. So it is 1 because the input is unit step input. Minus, okay, you can see here there is a sine part. Okay, so we can expect there will be a sine wave in the system. Okay, sine wave in the system. And then this part here, okay, it will be sine wave. Okay, and this part here will explain the damp energy. Okay, meaning how the damping will able to reduce the movement of the sine wave. Okay. So this is the time response equation for the second order, right? Okay. Okay. There is an additional here. Omega D is damped natural frequency, but we can calculate that based on the omega n zeta. Omega n multiply with square root 1 minus zeta square. Okay, and also there is a delay there. Okay, delay alpha is tangent inverse negative square root 1 zeta square over zeta. Okay, this is the phase shift. Okay, how the delay from the input to the output. All right, so we're going to discuss on the damping ratio, the effect of damping ratio, because we already know that for natural frequency, it's just a frequency that will cause the resonance to occur. So we just need to avoid that. We need to know because we want to avoid the reject. Okay, you will. There is no direct effect of omega n to the system, but when used together with the zeta, it will give some effect. Later we will see in an equation for each parameter that we're going to calculate. Okay, but for the damping ratio, there will be a direct effect onto the behavior of the system. Right. All right, so damping ratio is a parameter that we need to choose. Okay, so by choosing damping ratio, it will affect the behavior of the second order system. Okay, so there are three region of parameter that we can choose. The first one is what we call as overdamp, when we choose zeta is bigger than 1. Okay, so meaning there is higher energy in order to oppose the movement of the system. Okay, so if you choose zeta higher than 1, you can expect the behavior of the system to be like this. Okay, to be like the diagram here. Right, so you can see it will behave very much like first order system. Okay, yeah, like first order system. So first order system is something like this. Okay, but of course there will be the effect of this kind of behavior onto the system. Okay, for example, if you have for example in car suspension, okay, what happen if the spring is too hard, meaning the damping is quite hard there. So let's imagine that the spring is hard. Okay, the stiffness of the spring is quite high. Okay, so what happen if your car have a suspension like that? What do you feel? For example, if the car is run through a bump. Okay, anyone to share? What do you think you will feel if your car that have a like lorry hard spring suspension, like a lorry, okay, so run through a bumper, okay, without taking any precaution like slowing the vehicle, etc. Okay, you will feel the bump, right? The energy of the bump will transfer to your body. Okay, so there will be less comfort in that. Okay, because the energy is damped very fast, so the energy is transferred to our body. So it will relate to ride and comfort in a car. Okay, right. So that will be happen if you choose zeta damping ratio bigger than 1. Right. If you choose zeta equal to 0, meaning you're not putting any damped energy into your system. Okay, we call this as undamped system. Okay, so you can see that there will be no energy that trying to stop the movement of the system. Okay, so you can see that if the amplitude is if the amplitude here is 2, right? So it will have the same amplitude again and again. Okay, it's a sine wave and it will repeat the the wave again and again, because there is no energy that we're trying to damp the sine wave energy there. Okay, so when there is no damping, you can expect this kind of behavior. Okay, so the optimum value that we can choose for damping ratio is actually higher than 0 and lower than 1. Okay, so in case of a suspension system, we're choosing a good damping ratio within this region, bigger than 1 and lower than 1. So it will behave something like this. Okay, so you can see that the behavior will have some overshoot. Okay, so that the energy is not that straight away transferred to our body. So the overshoot will absorb the energy from the bump. Okay, and then the damping ratio will also slowly reduce the amplitude and then settle at the final value. Okay, this is the kind of behavior that we want from a second order system. Okay, we don't want it to behave like first order. Okay, we also don't want to have a very high amplitude of the sine wave. Okay, so by choosing zeta is bigger than 0 and lower than 1, we can adjust. Okay, we can adjust the behavior of the system, whether you want to have a higher oscillate system. Okay, okay, or faster response with only one peak there. Okay, the second one maybe, all right, we will allow some overshoot, but we want to have a faster response. Okay, maybe we want to have the overshoot is small, but we will allow it to have some vibration, and it will take some time to settle at the steady state final value. Okay, so it depends on the system. Okay, whether to have overshoot but have a faster settling time, or a lower overshoot, meaning the most important requirement is minimum overshoot, but we can allow for a longer settling time. Okay, or you want to have both combination, faster, lower overshoot and faster response, or higher overshoot, longer response. Okay, so the specification will depend on the requirement of the system. Okay, so the requirement of the system will help us to choose proper, meaning the optimum value of K, zeta, and omega n. And of course, we can expect the effect of K here is relate to the value of final value here. Y final. Okay, so the effect of K is similar to the first order system. So I'm not going to explain again. All right. Okay, any question related to this topic? Okay, no, from Amirul Hazin. All right. Okay, so let's continue. So for our second order or first order, actually it is the same, right? For the second order, okay, this kind of behavior is something that we're going to look into, right? So first is how fast the system responds toward the input. Okay, I mentioned just now we want a faster response. Okay, we want to have higher overshoot, lower overshoot, and settling time. Okay, so this is actually explained by these three indicator. Okay, the first one is how fast the system responds toward the input. Okay, so this one is given given by this one is given by what we call as rise time. Okay, TR. Okay, so we want to see how fast the system responds to the input. So we're going to look at a parameter named rise time. Okay, it is similar to the time constant. Okay, except the rise time. Okay, the rise time is time taken by the system in order to reach 100% output. Okay, so if we expect the final output is 1, okay, so it is the rise time is when the time when it reach 100%. Okay, so this is the one. Okay, rise time. You may also see a specification of 0 to 90%. Okay, sometimes they define 0 to 90 for their rise time. Okay, so you can have either way lah. Alright, so in order to calculate the rise time, alright, so this is the equation. Okay, alright. The second one is how much, how does the system oscillate? Okay, how does the system oscillate? Meaning how much oscillation occur in the system. This will be given by maximum overshoot and how many peak there are, which is T1, T2, T3, and etc. Okay, if there are many peak, then you have T1, T2, T3, T4, etc. Okay, so the peak will explain the oscillation of the system. Okay, right. So this is maximum overshoot. Okay, maximum overshoot is actually the difference between the value here to the final value. Okay, so the maximum overshoot is actually that region. Sorry, saya stop sekejap. Alright, sorry. Okay, let's start again. Alright, the second indicator is how does the system oscillate, which is given by maximum overshoot. So maximum overshoot is the difference between the highest peak, which is the first peak actually, highest peak minus the final value. So highest peak is here, okay, minus the final value, okay, the required value that we want, right? So the equation we give this difference here, right? And then we will calculate T1, okay, time to reach peak number 1, okay, T2, time to reach peak number 2. If you have another peak number 3, you want to calculate for peak number 3, then you can calculate for peak number 3, okay, 4 and 5. Okay, so you can see how this explains the oscillation that occur in the system. All right, and the last one is how long does it take to reach the final value? Okay, how long the time until the system, until the output will be stable at one final value. Okay, so that one is given by settling time. Okay, so this is settling time, TS. And then the settling time, there is also a specification for settling time, meaning we consider the system is reaching final value when the value is within the region of 2 to 5% above and below the final value. Okay, so if 1, so if it is already reaching 0.98, I think it is 2%, 0.98. So it is already considered to be reaching the final value. Okay. And the specification, meaning your system will define whether it is 2%, 3%, 4%, 5%. It will be based on the requirement of the system. Okay. Some system allow higher region, meaning 5%. Some system will have a very strict region, which is 2%. Right. So these three indicators, okay, and all these parameters, rise time, maximum overshoot, T1, T2, and settling time. Okay, if you're able to calculate that, meaning we will be able to sketch the behavior of the system, so we can see how the system responds. Okay, based on the parameter, we will be able to explain the behavior of the system. Right, so the first one is rise time. I already showed the equation there. Right, basically, before COVID, when we have face-to-face exam, the equation will not be given. Okay, but nowadays we have open book and not like open book, but maybe you can refer to the equation lah. Not very strict in terms of remembering the equation. All right, this is the equation for peak time. Okay, T1 is peak time for peak number 1. T2 is time for peak number 2. T3 is time for peak number 3. Right, so you can see the pattern there. Okay, you can also represent as pi over omega d. Okay, because omega n multiplied with 1 minus zeta square root is omega d. Okay, T1. T2 is 3 pi over omega d. And T3 is 5 pi over omega d. Alright, and maximum overshoot. Okay, this is the equation for percentage of maximum overshoot. Right, exponent negative zeta pi divided by 1 minus zeta square root. Okay. And then the last one is the equation for settling time. Okay. So the first one here is based on the acceptable limit. Okay. So your system, your design will determine whether it is 2%. 2% up until 5%. Okay, so you will determine that. Then you can calculate for the TS here. Okay, provided you have all the value, for zeta, omega n. Okay, you can see zeta here and also omega n. So if we have the value, then we can calculate for TS. Okay, based on the acceptable limit. Okay. As for the 2%, okay, okay, it's already the equation here is based on the equation, the acceptable limit. All right. So if it is 2%, then we can use this equation. Okay. So TS is approximately 4 over zeta omega n, depend on the value of zeta and omega n. In case of in case of test or final, if it's not mentioned 2%, 3%, 5%, just straight away use the 2% equation. Right, and this is the natural frequency of omega D. Okay, so that's all the parameters that we need to calculate in order to sketch the behavior of the second order system, and we can see the performance of second order system based on the parameters of the sketch. Okay, any question for the equations? Anyone want to ask? No. All right. Okay. Let's go to the example so that you can see, you can understand what I'm talking about. Okay. All right, so the first one here is a very simple one. This is how we determine the value k, zeta, and omega n from a transfer function. Okay, so given a transfer function of second order, okay, we know the second order because the order of the denominator is s squared. So this is the second order transfer function. All right, and then we're going to determine k, omega n, and zeta. Okay, so we need to compare with a standard transfer function, which is k omega n square over s square plus 2 zeta omega n s plus omega n square. Right? So we need to make sure that the parameter here must be 1. This is 1 here. It must be s square. Okay. So since this is already in s square, so we can directly get the equation there. So we have omega n square is equal to 9. Okay. Start here. Okay. 9 is equal to omega n square. Right, and then we have k omega n square is equal to 18. And the third equation will be 2 zeta omega n is equal to 3. Okay, 3. Okay, so by having these 3 equations, we can determine the value for k, zeta, and omega n. Okay, so therefore omega n here is equal to 3. And then k will equal to 18 divided by 3 is 6. Okay, and then zeta will equal to 3 divided by 3 divided by 2, which is 0.5. Okay, this is k, this is 3 radian per second. Okay.
Doctor, should k be 2? Because...
Okay, yes, k to be 2. 2 kali 9, 18. Okay, sorry. Correct. Thank you. Okay, 2. All right, omega n will have parameter radian per second. K is again, there is no unit there. And zeta is a ratio, then there is no unit there. All right, so that's how we determine the value of k, zeta, and omega n, because we need to know zeta, omega n in order to calculate all the parameters that all the parameters like rise time, settling time, T1, T2, and also maximum overshoot. All right. Okay, example 2. Okay, in this example number 2, you're going to calculate. Okay, you're going to calculate omega d. First and second peak, which is T1 and T2, and then percentage of overshoot, MP percentage. Okay, so we have the equations. Okay, and all the equations will require a value of zeta and omega n. Okay, so here the zeta is given, zeta and omega n is given. So we just going to use directly in the equation, right? But sometimes they give you the transfer function, so you need to determine the value from the transfer function. Alright, so just calculate the omega d. So if you know the equation, so I think it just a matter of putting the value into the equation. Right, T1 is pi over omega d. T2 is 3 pi over omega d. And then maximum overshoot is exponent negative zeta pi. Exponent negative zeta pi over 1 minus zeta square. Square root. Okay, so just put the value of zeta and omega n into the equation. So you should get the value. The square root zeta pi. All right. Tolong Kak ambil. Okay, what is the value for omega d?
11.76.
Same.
Right, 11.76 radian per second. T1?
0.27.
0.27 second. T2?
0.8.
0.8 second. And MP? Okay, so if you're going to plot the behavior, okay, let's consider the final value is 1. All right, what is the value for MP?
52.7%.
52.7%. All right. So it will occur at 0.27 seconds. So let's say this is 0.5. This is 1. Right, 0.27 will be around here. 5 to 7, around here. All right. And then 0.8 will be around here. All right, 52.7%, which is equivalent to 0.57. Okay. Right. So we can expect the okay, right. Wait. Okay. Let's say here is 1. Okay. Okay, I'm just going to sketch the response. Okay, so at T1 it will reach 1.527. Okay, so around here 1.527. Okay. Alright, so we can have something like this. Okay, we can expect the behavior like that. Okay, because we're not calculating the rise time. We're also not calculating the settling time. But by sketching, we can expect the behavior like that, like this. There will be two peak because it asks to calculate two peaks. So we're going to sketch for two peak. Okay, the time for peak number 1 here is 0.27, and time for peak number 2 is 0.8. Okay, and then based on the maximum overshoot that reached 52.7%, meaning in term without percent it is 0.527. So this is the value of 0.527. Right, the difference between the peak and the final value. So we can expect the peak to be at 1.527. Okay. All right, so we have the equation. Okay, we can calculate the parameters if we have the value of zeta and omega n. All right. Example 3. We have example 3. There is one more example. Okay, example 3. Okay, in this example here. All right. For proportional value Kp20, determine the natural frequency, percentage of overshoot, and settling time for the system if the unit is the input unit sample. All right. So in this example here, the student will need to understand. We need to understand how can we get the value of zeta and omega n. Okay. Because it is actually you need to determine the natural frequency, okay, percentage of overshoot, and settling time. Okay, so in order to calculate for MP and settling time, we will require the value of zeta and omega n. Okay, so we need that. So having a block diagram like this, how can we determine the value of K, zeta, and omega n? Okay, so the first concept that you need to understand is, okay, for time response analysis, okay, we will use the closed loop transfer function. I believe I already explained about open loop transfer function and closed loop transfer function during the classification topic. Okay, I said that for classification, it is based on the open loop transfer function. So you already know how to determine the open loop transfer function. And for the time response analysis, it will be based on the closed loop transfer function. And I believe you already know how to get the closed loop transfer function, okay, which is closed loop transfer function is given by kg over 1 plus kgh. Okay, I believe you're already familiar with this equation. Okay, so we consider this is K, this is G, and this is H. Okay, so by putting the value of K, G, and H into the closed loop transfer function, we get we can determine the value of zeta and omega n. Okay, so let's do that. Okay, so let's say Kp is 20. Okay, what will be the value? Kp 20 multiplied with 1.2. 1.2 is 24. So Kg is 24 over S plus 1 multiplied with 0.2 S plus 1. Okay. Divide by 1 plus 24 multiply with s plus 1, 0.2s plus 1, multiply with h, which is 1.6. Okay, so if you do the block diagram, you practice on block diagram manipulation, you will know you're going to multiply to here so that you can cancel this term together. So you will left with 24 divided by 0.2s square, okay, 0.2s square plus s plus 0.2, 1.2s plus 1, and then 24 divided by 6 is apa? 24 divided by 6, 6 kali 4 kan? 6 kali 4, so tambah 4 lah. So the final transfer function will be 24 divided by 0.2 second square plus 1.2 second plus 5. Okay. Right, so we get the closed loop transfer function. All right. Okay. But we cannot determine k and omega n and zeta yet because the transfer function is not in standard form. Okay, so in order to convert into standard form, all right, so we need to convert into standard form of a standard transfer function of second order system, because here we have 0.2. So we need to divide by 0.2 because we want to make sure that the parameter for s square must be 1. So we divide all the term with 0.2. Okay. So 24 divided by 0.2 is 120. So meaning the closed loop transfer function will be 120 divided by s square plus, okay, 1.2 divided by 0.2 is 6s plus 5 divided by 0.2 is 25. Okay, so now it is in standard form, okay, because here it's only s square, 1s square there, okay. So we can determine the value of zeta and omega n. Okay, so we can say omega n square is equal to 25, right? And then k omega n square is equal to 120, and then 2 zeta omega n is equal to 6. Okay, so you'll be able to determine the value of omega n, k, and zeta. So of course, later you will be able to calculate for the maximum overshoot and settling time. Okay, so I'm not going to show you all the calculation. All right, any question? I hope everything is clear. All right, so you just need to understand, we need to we need to determine the value of the parameter, which is zeta, omega n, and k, which is based on the closed loop transfer function. Okay, sometimes they will not give you the block diagram, they will just give you a statement. So you need to be able to understand the statement and represent it into a block diagram. Okay, if it's given to the in terms of block diagram, so you need to know that the closed loop transfer function is kg over 1 plus kgh. So why we need closed loop transfer function? Because the time response analysis will be based on the closed loop transfer function. Okay, based on the closed loop transfer function, we can determine the value of k, zeta, and omega n, and it must be in a standard form of second order transfer function. Okay. Okay. All right. So last one, example number 4. Okay. Okay. In the previous example, okay, example 1, 2, and 3, okay, they give you transfer function. Okay. Okay, the flow is transfer function, closed loop transfer function. Closed loop transfer function. All right. Then from this closed loop transfer function, you determine K, omega n, zeta. And then you'll be able to calculate TR, NP, T1, T2, TS, settling time. Okay. All right. But in this example here, they give you the specification. Okay. The specification meaning in terms of TR, MP, T1, T2, and settling time. Okay. So you need to determine the K, zeta, and omega n from the specification. Then and then you need to determine the transfer function. Okay. So the flow will be reversed. Right, so the specification given in this example is, okay, fastest response with percentage overshoot less than 5% and settling time less than 4 seconds. Okay, so meaning it based on the maximum overshoot and settling time. Okay. So we know the equation for settling time and overshoot. Settling time and overshoot. Right. So MP is equal to exponent negative zeta pi over square root 1 minus zeta square. Okay. So if you multiply with 100, so it will be percentage. Okay, so based on the requirement, so the equation will be 5%. Okay, less than. Less than 5%. Okay, okay. Okay, less than 5%. That is the first requirement, right? And for the second requirement, okay, design specification, they require the system to have settling time less than 4 seconds. Okay, meaning you need to reach final value, you need to settle to the final value less than 4 seconds. Okay, so the equation for settling time is considering 2%, it is 4 over zeta omega n. Okay, so we use this equation. Okay, 2% equation. All right, so we said that settling time 4 over zeta omega n must be less than 4 seconds. All right. So based on these two specification, we need to determine the value of zeta and zeta omega n and k. Okay, but basically it is zeta omega n first. Later we will determine k. Okay, so we're going to start with maximum overshoot because in the equation for maximum overshoot, it only based on the zeta. Okay, only one parameter that determine the maximum overshoot, which is based on zeta only. There is no omega n in the equation. So we have one equation, one parameter, so we can solve for zeta from this equation. Okay, but for the settling time, it will require two parameter, zeta and omega n, but we have one equation only, so we cannot solve from settling time. Okay, we need to solve from maximum overshoot first, then we put into settling time equation, then we determine omega n. Right, so therefore less than 5%, meaning exponent negative zeta pi over square root 1 minus zeta square will be equal to 0.05. Okay, we just omit the percent here. Okay, so you know how to cancel the exponent. Okay, we're going to ln all this exponent negative zeta pi over 1 square root zeta square root equal to ln 0.05. Okay, so by having ln, we can cancel exponent there. Okay, so just continue to calculate. Okay, just continue to calculate. You will get zeta. Okay, please calculate and tell me the value of zeta. It's not, it must be less here. Less. Okay, you will have zeta pi. Kacau. Hilang pula calculator. Mana ln 0.05? What is the value for ln 0.05?
Negative 2.996.
2.99 boleh betul. Alright, so we're going to square all this. Okay, so we cancel this. Right, so we have zeta pi square must be less than 3.99 square is tahulah tuan, you calculate, tolong bagi saya zeta sahaja. Mana calculator ni tadi? Okay, so it's around 0.66. Right, so we need to choose zeta. The value of the zeta must be less 0.66 in order to get the fastest response that less than 5%. Okay, maximum 5%, you need to choose 0.66. All right, so put into the settling time equation, you should get omega n. Omega n is bigger than 4 divided by 4 multiplied with 0.66. So omega n must be bigger than 4 divided by 0.66. 1.5 to 18%. All right, so for the natural frequency, you need to choose omega n that is higher, bigger than 1.52 radian per second in order to get settling time around less than 4 seconds. Okay. Okay, so we have the value of zeta, omega n, right? So we need to get the transfer function because we need to determine the value of K and P. Okay, so SS plus S plus P. So let's go to okay. So we have a transfer function of K over S, S plus P, right? And then we have a negative feedback loop, right? Without H1, right? So just consider this as kg. All right, so the closed loop transfer function will be kg over 1 plus kgh, and h is considered as 1, right? So that will equal to k over s plus p divided by 1 plus k over s plus p. Okay, similar, we can cancel this by multiplying to here. So the closed loop transfer function will become k over s squared plus ps plus k. Okay, so that is the closed loop transfer function. So we're going to determine okay. So from here we know that K, okay. So if we compare with K omega n square over zeta square plus 2 zeta omega n s plus omega n square, right? So we can say that K is equal to omega n square, and then K omega n square is equal to K, and then 2 zeta omega n is equal to P. Okay, so we can determine K and K as in the parameter, K in the system, and also P, and then also the gain of the system. Okay, but basically gain here is 1. This is 1. Okay, so we have the value of omega n. So K is equal to 1.52. Is it? I don't remember. Berapa value omega n tadi kita calculate?
1.52.
Okay, 1.52 square. So that is the value for K. And then as for P, it is 2 multiplied with 0.66 multiplied with 1.52. Okay, this will be equal to P. Okay, so you can see the flow is reversed. They give you the specification. It gives you the parameter, actually, the maximum overshoot. It gives you settling time. So we determine the value of zeta and omega n from there. Okay, and then we're going to design the value of transfer function based on that. Okay, so here you need to choose a value of K and P as in the system, transfer function of the system. So we do that by comparing to the relationship between transfer function of second order to the transfer function of a system. Okay. Any question?
No.
No, Amirul. Right. Okay, if no question, let's have 5-minute breaks. Then we're going to continue with steady state error. Anyone? Can we start?
Yes, Doctor.
Yes, Doctor.
Okay, thank you.
Yes, Doctor.
Thank you. Okay. It's better to have some communication rather than talking to the computer alone. All right. Okay, so in previous topic, first order and second order, all the parameters, all the behavior that we have discussed is actually for a part of transient region. Okay. In the very first part, when I introduced you to time response analysis, I mentioned that time response analysis will be divided by 2 parts. The first one is transient region, and the second part is the steady state region. Okay, transient region is when the system change dynamically due to the input. Okay, and then it will settle to one final value, which is what we call as a steady state. All right, so either time constant, that is the parameter for first order for the transient region. Okay, and as for the second order, it is rise time, settling time, maximum overshoot, T1, T2, and settling time. That is for the transient region for the second order system. Right. So for the steady state region, okay. So in order to study the behavior of any control system at a steady state, we're going to study the steady state error. Okay, we want to know how much error, which is the difference between the required input, the required output that we want, to the actual output. Okay, so the difference is what we call as error. Okay, so let's say it is unit step input, meaning we want the system to settle at 1. Okay, but if it settled at 0.9, meaning there is 0.1 error. So that is what we call as steady state error. Okay, so if the error is big, by comparing the steady state error, we will able to compare the performance of the system. All right, so in order to derive the time response equation for the steady state error, right? So in order to derive the time response equation for the steady state error, we will require a steady state equation. Okay, steady state transfer function lah. Alright. So based on the relationship here where we have, okay, so here we have error, okay, so we can write error is actually the difference between US minus Y multiplied with HS. So here Y, or sometimes we write the transfer function first, multiply with Y. Right, so it is H in Laplace multiply with Y. Right, so put Y and S. Right, and then based on the diagram here also, we can say that okay, as for the YS, okay, based on this part here only, okay, so we can say that YS is equal to GS multiply with ES. Right, the input error is ES multiply with the transfer function GS, we give us YS. Alright, so let's put YS into the ES equation. So we have ES is equal to US minus HS multiply with GS multiply with ES. Alright, ES. Alright, so we can have ES plus GHS multiply with ES is equal to US. Okay, so we have ES, factor the ES, so 1 plus GHS equal to US. Okay, so the output is error ES, the input is US, so the transfer function is ES is equal to 1 over 1 plus GHS multiply with US. Right, so we can derive the time response equation for the error if we multiply, if we replace US for any input, let's say step input, ramp input, etc. And then we do all the process there. We do the partial fraction, we determine the parameters, and then we get ET equal to something. Okay. All right. But we're not going to do that because we only interested at the steady state. Meaning, if we plot the time response for the error equation, it will give you something like this. Okay, the error may start at bigger, and then it will slowly settle to one final value. Okay. Or the error is 0, or there is some error here. So this is what we call as steady state error. Okay, the difference between, of course, we require the error to be 0. Okay, the objective is error to be 0. But sometimes the system, based on the design of the system will not be able to reach the required set point. Okay, so it will settle at any value. Then the difference between that will be called as steady state error. All right, so we're not interested. Okay, we're not interested to this region. We don't want to know that because there will be some fluctuation and etc. Okay, we want to know the value of this one only. Okay, so due to that reason, we're not going to derive the error, the time response equation for error. Okay, instead we're going to use final value theorem. Okay, so final value theorem will allow us to get any final value. All right. So how to apply final value theorem? Okay. So in final value theorem, we consider time is approximately infinity. Okay. So in Laplace, infinity meaning s goes to 0, meaning we approximate s equal to 0. Okay. So final value theorem said that for a steady state error equation, we're going to apply limit t to infinity, meaning we expect t is equal to infinity into the error function, right? And in Laplace, it is equal to, we consider limit s equal to 0 for s multiplied with the error equation. Okay, s multiplied with the error equation. We already have the error equation. So ES just now is 1 over 1 plus GHS multiplied with US. Okay, so we just need to multiply with S, then we apply limit S equal to 0. Okay, so we have this. Okay, so we can see that final value theorem said the equation for steady state error is equal to, we apply limit S equal to 0. Okay, S over 1 plus GHS multiply with US. Okay. Okay, so far? All right. Okay, so looking at this equation, we can see that the steady state error is depend to two parameters. Okay, the first one is type of input. Okay, the value of steady state error will depend on the type of input. Whether you apply step input, ramp input, parabolic input, okay, it will give you different steady state error. Okay, the second parameter is this part here. Okay, this part here is what we call as is equal to open loop transfer function. Okay, GHS is considered as open loop transfer function. Or sometimes we have KGHS. Okay. Okay, so meaning the steady state error will also depend on the class of the steady state error. Okay, class of steady state error. Class of open loop transfer function. Okay, directly we say it based on the open loop transfer function, but actually it is based on the class of open loop transfer function. Right. Okay, so it depends on the type of input and open loop transfer function. All right. Okay, so we're going to apply three types of input. The first one is step input, where US will equal to 1 over S. And then the second one is ramp input, US equal to 1 over S square. And the parabolic input, US equal to 1 over S cube. Okay. I'm going to use here because there will not enough space in that. Is it okay to have black and white? Or you prefer white background and black color?
Okay.
Okay, Ada.
No.
Yeah. All right. All right. So let's write the equation for error is equal to, based on the final value theorem, we will apply S goes to 0 for S multiplied with the error equation, which is 1 over 1 plus GHS multiplied with US. All right. So for the first one is for step input. I'm going to apply for step input, where US is equal to 1 over S. Okay, so we do that. So bukan error S. I'm not supposed to write error S here. It is steady state error. Steady state error, we equal to limit S goes to 0, S over 1 plus GHS multiply with 1 over S. Okay, so we're going to cancel this. All right, so it left to limit S goes to 0, 1 over 1 plus GHS. Right? So we can simplify the equation to be steady state error for a system that is applying unit step input. The steady state error value will be 1 over 1 plus Kp. Okay, where Kp is equal to limit S goes to 0, GHS. Okay, and the Kp here is also known as, nama dia, the name for the Kp is displacement error constant. Displacement alright, so meaning here, if you have a system, any system, right, and then you want to calculate the steady state error, and then the input is unit step input, okay, you can calculate the steady state error by using 1 over 1 plus Kp, okay, where Kp is the displacement error constant, is calculated using a limit S goes to 0 for the open loop transfer function of the system. Okay, meaning you need to determine the open loop transfer function of the system, and then you're going to apply a limit S goes to 0 to the open loop transfer function. Okay, so it will give you some value. Okay, so let's say, for example, let's say this is, okay, just now, before this, I said that it is based on the, later saya explain. Let's just took one example. Okay, let's say the open loop transfer function of a system is 1 over S plus 1. Okay, so therefore we can determine Kp. Kp will be equal to limit S goes to 0 onto the open loop transfer function S plus 1. Okay, so meaning we apply limit S goes to 0 is that we actually consider the value of S is 0. Okay, so any S in the open loop transfer function will become 0. Okay, so therefore Kp is equal to 1 over 1. So it is 1. Right? So based on the open loop transfer function, we apply S goes to 0 onto all the term of S in the open loop transfer function, we get the value of Kp. So from there, we're able to calculate steady state error is equal to 1 over 1 plus Kp, which is equal to 1 over 1 plus 1, 1 plus 1 equal to 2, 1 over 2. So it will give you the error 0.5. Okay. Okay, so a conclusion for this, for any system, okay, when you apply unit step input, okay, you can expect the steady state error to become to be a value. Okay, meaning you can determine the steady state error. Okay, the steady state error is 1 over 1 plus Kp. Okay, so Kp is limit s goes to 0 to the open loop transfer function. And here in this example, we have 0.5. Okay, so we can expect the system to have to behave like this. We expect the system to reach 1 because it's unit step input, but instead the system will only reach 0.5. Okay, because the steady state error equal to 0.5. Okay, meaning 1 minus the error, 1 is the final value, minus the error 0.5, so the final value is 0.5. Okay, so this is for the first case when we apply step input. Okay, any question? Right. No question. Let's continue with the second input. Okay, second input is RAM input. US equal to 1 over S square. Okay. Right. So again, we do the same. Steady state error is equal to limit S goes to 0. S divide by 1 plus GHS multiply with the input, which is 1 over S square. So meaning it give you limit S goes to 0. We can cancel this. Okay, so it become 1 over S plus SGHS. Okay, so if you apply limit to S, this one will become 0. Okay, so it will left with 1 over limit S goes to 0 for the SGHS. Okay, so that is the steady state error. And then we can simplify the equation to become 1 over kV. The steady state error, when you apply a RAM input, is equal to 1 over kV, where the kV is velocity error constant. Okay, and we can calculate velocity error constant by applying limit S goes to 0, S multiply with the open loop transfer function. Okay, this part here. Okay, so that is when we apply a system, when we apply a RAM input into any control system. So we can predict the steady state error to become 1 over kV. Right, last one is C when we apply a parabolic input. US is equal to 1 over S cube. Okay, you will do the same process again, where you eventually get error, steady state error. Okay, steady state error is equal to 1 over Ka, where Ka is equal to acceleration error constant. Acceleration error constant. Okay, and then okay, and we can calculate Ka by applying limit S goes to 0, where we multiply S square with the open loop transfer function. All right, so this is how the input, type of input will affect the calculation of steady state error. Okay. Ambil ni tolong. All right, for the second part, I said that the steady state error will also depend on the class of the open loop transfer function. Okay. Right. So in this table here, we can see that, okay, let's just focus on the step input first. Okay. So if we apply step input onto any control system and the open loop transfer function of the system is class 0, okay, the transfer function is having class 0, okay, so you can expect the error, the steady state error, to be a value 1/1 plus Kp, right? If the system is having a class 1 0, is having a class 1, okay, then the steady state error will become 0, okay, and it's also true for the class 2 and higher, class 3, class 4 and higher, okay, we can expect the error to be 0, okay. So we have proof for this one just now, okay, in the example just now, okay. So the open loop transfer function is s plus 1, so this is class 0, right? Because class is the highest factorial of s of the denominator, okay. So we look at the denominator and we try to factor the s and then the order of the s will determine the class, okay. Or another way is to look at the last term of the denominator. So if it is the number, it is a number 1, 2, 10, 100, okay, so it is class 0, okay. So this is the example of class 0 transfer function. Class 0. Right, so for class 0, we have applied limit s equals to 0, and then we calculate, we get 0.5. Okay, let's say that the value here is 2. Okay, so this one will become 2. Okay, so this is 2, this is 0.5. Okay, this also become 1.5. Okay, and then the error will become 1 minus 1.5 divided by 0.66. 0.66. Okay, the error will become bigger. Okay, so the conclusion here, for a class 0, when we apply a unit step, when we apply step input, it doesn't necessarily unit step input. When we apply step input, okay, we can have, there will be a value for the steady state error. Okay, it can be 0.1, it can be 0.6, it can be 0.5, it can be 0.4, any value. Meaning it will be a value, any value. Okay, all right. Based on the table just now, if it is class 1, the steady state error will become 0. Okay, let's try for class 1. All right, let's try for class 1. Okay, so for class 1, the open loop transfer function, let's say the open loop transfer function is 20 over s plus 5. Okay, right, so we're going to calculate the steady state error. So the steady state error is equal to 1/1 plus Kp. Okay, so the Kp, we're going to apply limit S goes to 0 onto the open loop transfer function, which is 20 over S plus 5. Okay, so we're going to apply the S there. So this will become 0, this will become 0. 20 divided by 0. 20 divided by 0 is infinity, right? Okay, so therefore, the steady state error is equal to 1 over 1 plus infinity, which is equal to 1 over infinity, which is equal to 0. Okay. Right, so that's how we prove for the part here. Okay, for class 1, the steady state error is 0. Okay, it will be similar to class 2, 3, and 4. The higher the order, okay, because there will be S term at the bottom there, multiply with S square, meaning you need to multiply with 0. So it will always become, the KP will always become infinity. So the error will always become 0. Okay. As for the class 0, there is no S to be multiplied with, so it will have a value. Okay, so that's why the value will always occur. So it is 1 over a value, 1 plus something. Okay. So the error will always there for this step input. Okay. Any question? All right. So if you do for the all right. Let's just show for the last part there, not last part, for KV. Okay, so we apply a RAM input. Okay, so RAM input, we know the equation, the steady state error will equal to 1 over KV, or 1 over limit S goes to 0. Okay, limit S goes to 0. S multiply with GHS. Okay, so we have derived this. Okay, so let's consider for class 1, class 0. So let's consider the GHS is 1 over S plus 1. Okay, class 0. Okay, so we're going to apply limit to the, so we're going to calculate for KV. So KV is limit S goes to 0. S multiply with 1 over S plus 1. Okay, so therefore this one becomes 0 and this one will become 0. So it is equal to 0 over 1. So 0 over 1 is 0, right? Okay, so therefore the steady state error is equal to 1 over KV, which is equal to 1 over 0. So you get infinity. Okay, so that is for KV. Right, and similarly we can also prove for class 1. GHS equal to 1 over S plus 1. This is class 1. So you do the same. Okay, so you can expect there will be a value because S here will be cancelled. This S here will be cancelled with the lower S here. Right, so therefore it will have 1 over a value. Okay, so that's why the error will become 1 over KV, a value. Okay, all right, and then it becomes similar to the parabolic input. Okay, so meaning you'll be able to prove this table. Okay. Questions, guys? You diam je, tak tahulah faham ke tak faham ke. Tak ada.
Doktor
Okey,
boleh
Doktor.
balik tak yang parabolic input?
Parabolic input. Parabolic input is the same. Okay. I just want you to do because we have this is parabolic input. I'm just going to show the first part only. The steady state error is 1 over Ka, where 1 over Ka is 1 over limit s goes to 0, s square multiply with GHS. Okay, so if it is class 0, okay, class 0, 1 over s plus 1. Okay, so the s square here, okay, s square here will become 0. Okay, because if you multiply, it will become s square over s plus 1. Okay, when we apply the limit, this becomes 0. Okay, this one becomes 0. So it is always 0 over something. 0 over 1, 0 over a value. So that will always give you 0. Okay, then later when you calculate for steady state error, it is 1 over 0. So that is will always be infinity. Okay, so it only become a value if we able to cancel this 0 square here. Okay, so in order to be able to cancel s square, okay, because it will become GHS, s square multiplied with GHS. So there will be always s square. So it need to be the second order. Okay, so s square plus s square plus what? S square multiplied with s plus 3. Okay, the open loop transfer function is actually 1 over s square over multiplied with s plus 3. Okay, and it is a second class, class 2 classification is class 2 because the highest factorized is s square, and here we can see we can cancel that term. So it will become 1 over s plus 3. This will become 0, apply the limit. So there will be a value 1 over 3. Okay, so that is for parabolic input. Okay, just do this the process step by step. I think you can extract the information from there. You can extract the understanding from there. All right, so let's calculate for the error constant and steady state error for a system with open loop transfer function. Basically, we already done this. Okay, so we know that it said displacement error constant, meaning this is Kp, right? So Kp is equal to limit s goes to 0, open loop transfer function. So 10 over s plus 20. Okay, so therefore this is 0. So we have 10 over 20. It's 0.5. Okay, so the steady state error is 1 over 1 plus Kp. So it is 1 over 1.5. So similar to just now, 0.67. Okay. Right. Okay, so we have the equation for Kp. Kp is limit s goes to 0 open on the open loop transfer function. Okay, so we're going to apply that. We get the value of Kp, put into the equation of steady state error, 1 over 1 plus Kp. So we get the steady state error. All right. So for example 2 here, you need to calculate for error constant, meaning you need to find for Kp, Kv, and Ka. Right? So we already know the equation for that. So Kp is limit, we apply limit s goes to 0 for the open loop transfer function. Okay. KV is we apply limit s goes to 0 where s multiply with the open loop transfer function. This is based on the derivation that we have done just now. And last one is KA is limit s goes to 0, s square multiply with GHS. Right, so therefore you need to determine the open loop transfer function. Okay, so open loop transfer function is equal to KGH. So this is K, this is G, this is H. Right, so if you're able to solve for the open loop transfer function, then you can calculate for KP, KV, and KA by applying S goes to 0 to that. Okay, so for the open loop transfer function, it is equal to 3K plus 4 over 3 multiply with 1 over S cube. You boleh solve lah ni. 10S square plus 16S. Okay, so you get the transfer function. Okay, S is considered equal to 1. Apa dapat So it is 3K plus 4 divided by 3S square plus 30S square plus 16 kali 3, 48 48S. Okay, so by looking at the denominator, we know this is class 1. Okay, but we're not going to calculate the steady state error. We're just going to calculate the KP, KA, and KV. Okay, so you can do the limit. KP is equal to limit S goes to 0 on the 3K plus 4 divided by 3S plus 30S square plus 48S. Okay. Let me just show one. Okay. Right, when you apply this becomes 0, this one becomes 0, and this one becomes 0. Okay. So a value here, this is a value, 3K. Let's say K is 1. So it is 7 divided by 0, we give you, bagi kosong apa? Infinity. Infinity. Okay, infinity. Right, so KP is infinity. Right, so then you do the same for KV and KA. Okay, so we can expect KV will have some value and KA to be 0. KA to be 0. Okay, because we can cancel S, we factorize S, we can cancel S, so it become a value, and this one we cannot cancel, so then the numerator we have a 0. So 0 divided by something is infinity. 0 divided by something is 0. Okay, so we can expect KV to have some value. We can calculate the value. And KA will become 0. Okay? Alright. Alright, so it's 10 o'clock. So if you have class, you can leave. If you have questions, you can ask.
Thank you, Doctor.
Right, thank you.
Thank you, Doctor.